A warm welcome to the 25th lecture on the subject of digital signal processing and its applications. We begin with another aspect of infinite impulse response filter design today. So far we have designed the Butterworth and the Chebyshev low pass approximations for the analog domain. Now we would like to design other kinds of piecewise constant filters of importance, namely high pass, band pass and band stop. We have of course assumed that we have brought the specifications into the analog domain already. So using the bilinear transform, we have put down the specifications of the analog filter that we wish to design, whether it's high pass or band stop. But now we wish to get down to actually designing the analog filter of given nature with appropriate nature for the pass band and stop band. By nature I mean equiripple or monotonic. So we want the nature and the type of the filter, that is the kind of bands in the filter, to be designed explicitly. So therefore the process that we are going to follow is to, again, as we have done before, take advantage of the designs that we have until date and then use those designs to go further to build other kinds of filters. So we have already designed Butterworth and Chebyshev low pass filters. Now we would like to use a transformation on these low pass filters to get filters of other kinds, and therefore what we are going to do today is to discuss frequency transformations in the analog domain. Now, as the name suggests, frequency transformations essentially refers to a transformation on sinusoidal frequencies. And sinusoidal frequencies come from the imaginary axis in the S plane. So what we expect is a transformation that goes from the imaginary axis to the imaginary axis. And of course the transformation must obey certain requirements. Let us first put down what we mean by a frequency transformation and what we insist that it should obey. So what do we want of an analog frequency transformation? We want three things once again, as we did when we went from analog to digital or digital to analog. The first thing that we want is preservation of rationality. So essentially what you are saying is that if you denote the complex frequency variable for the low pass filter by SL, then you need a transformation on SL. Now please note, so far we have always been just writing S for the complex frequency variable of the analog filter. But now what we are saying is we want indeed to have the complex frequency variable S, the Laplace variable S. But then you want to go through an intermediate step. You want to design a low pass filter and you want to replace the complex frequency variable S in the low pass filter by another function of S. So we need to distinguish between these two variables. The complex frequency variable in the low pass filter shall therefore henceforth be referred to as SL, S sub L, and S corresponds to the complex frequency variable in the filter of desired nature. This is what we mean by an analog frequency transformation. Replace the complex frequency variable in the low pass filter by an appropriate function of S. And obviously, if you want rationality to be preserved, so if you want the low pass filter, which is of course an analog rational function, to continue to be a rational function after the transformation, the only way is that Fs itself must be rational. So F must be rational. There is no choice. Of course, we don't need it to be bilinear, or we don't need it to be first degree. It could be any degree, that doesn't matter, but it has to be rational. Secondly, we want it to preserve stability. And that implies a correspondence between left half planes and right half plane. You see, it is the left half plane and the right half plane in S, in the complex, in the Laplace variable S, that determines stability or otherwise. So we need left half plane to left half plane and right half plane to right half plane mapping. That would ensure that if the low pass filter is stable as it is, then this transformation would not create an unstable analog system due to the rational change. Finally, we need a correspondence between the imaginary axis. After all, we are talking about a sinusoidal frequency transformation. We want the imaginary axis to go to the imaginary axis, otherwise there is no meaning in this transformation. After all, what we want is that a certain set of specifications on the kind of filter that you want to design should translate into corresponding frequency domain specifications for the low pass filter. So the absolutely essential thing is that sinusoidal frequencies from the filter of desired nature must go into sinusoidal frequencies of the low pass filter, and that implies that the imaginary axis in the S plane must go on to the imaginary axis in the SL plane. Now, we might ask, what is a transformation, or what is a set of transformations that meets all these requirements, and how do we search for such transformations? Here again, our experience of analog functions should come to our aid. You see, after all, if we just reflect a little bit, what are those analog functions of S? Let's begin with the third requirement. What are those analog functions of S, which when you substitute S equal to j omega give you imaginary quantities in SL? You know, it immediately rings a bell if we think of impedances. We might always visualize the function f of S to be an impedance or an admittance, and if we do that, then it immediately rings a bell if we ask that S equal to j omega should put us onto the imaginary axis. In other words, that the impedance must be imaginary or the admittance must be imaginary. We know what kind of networks give us imaginary impedances. Essentially, networks that comprise only of capacitors or inductors. So, the first clue that we get from the third requirement, it is clear that we are asking for Fs to be the impedance or admittance of an LC network, a network comprising only of inductances and capacitances. And of course, we might ask whether if we do indeed choose such LC impedances, they satisfy the other two properties as well, and we are fortunate actually that they do. Now, the property of moving from the left half to the left half and the right half to the right half is actually a very important property of all impedance and admittance functions. It is called the property of positive realness. Many of us might have encountered this property when we dealt with network theory, network synthesis in particular, but we probably have never looked at it from that perspective. What we are saying in effect for property 2 we want real part of Fs to have the same sign as real part of S. And that is essentially a so-called positive real property of network function. So, even without explicitly verifying this property, if we do indeed use LC networks, we are very likely to be satisfying this implicitly by design. But we shall, when we look at the frequency transformations, explicitly verify this property for each of them. However, this tells us this positive real property of impedance or admittance functions assures us that we are likely to succeed in that endeavor. Finally, we go to the first of the requirements, rationality. Now, rationality is not a problem at all. The impedance or the admittance of LC networks is of course rational in S. So, we don't need to worry about that at all. So, with that then we have all the properties satisfied, and we can look at the simplest of the three possibilities. We wish to go from low pass to high pass, low pass to band stop, low pass to band pass. And therefore, the simplest of them, as we expect, is low pass to high pass, because in a certain sense, when we go from low pass to high pass, what we are doing is to reverse the roles of frequencies in a way. I will explain what I mean. High pass transformation. Now, you see, in a high pass transform, what we wish is that as the frequency increases, in a high pass filter, we have a specification something like this. So, you would expect that you would have a stop band and then a pass band like this. So, what we are saying is, as we go from 0 towards plus infinity, and of course, the same thing is mirrored on the negative side, we do not need to keep drawing the negative side. As we go from 0 to infinity on the omega axis, we expect that we first encounter the stop band and then the pass band. So, it is very clear that if I want to go from here to a response like this, as I had for the low pass filter, then I should be traversing the frequencies in the opposite direction. So, when I move this way on the high pass frequency axis, I should be moving this way on the low pass frequency axis. That is what it sort of suggests to us, that we want an inversion of behavior. And then it is very easy to think of an admittance which gives me inversion. Either the admittance of an inductor or the impedance of a capacitor gives me inversion. So, all that we need to do is to consider a transform like this. F high pass S is of the form omega p by S, simple, inspired by inductance, admittance of an inductance or impedance of capacitance. Now let us verify what this does to us. Let us start with the last property first. Let us see what it does to the imaginary axis. Let us put S equal to j omega. So what we are doing essentially is we are going to replace omega, or rather we are going to replace SL of the low pass filter by omega p by S. So what would we get? When we put S equal to j omega, we would get omega p by j omega L, by j omega, which is minus j omega p by omega. And this is of the form j omega L with omega L equal to minus omega p by omega. So indeed, the sinusoidal frequency behaves as we expect it to, and that was not surprising. You have taken an LC impedance anyway. It is bound to have an imaginary impedance. But the good thing is, if you now look at the way the frequency changes, so let's draw what we call the frequency plot, the frequency transform, the sinusoidal frequency transform, or the frequency mapping. These are different names that are used for this. So the sinusoidal frequency mapping. So what we do in a sinusoidal frequency map is we take omega and map it to omega L. Of course, we know that omega L is minus omega p by omega. So what we are saying essentially is, as omega goes, you see, you want this is the kind of response that you want in the high pass filter. Now omega p would map to minus 1. Omega s is less than omega p, and therefore minus omega p by omega s is a quantity less than minus 1. So it is behind minus 1. So there we are. Omega s would map there. And of course 0. Now we must be careful about 0. We don't really go to 0, we say 0 plus. 0 plus means a very small positive value. And you can make that small as you desire to move to 0. So very small positive value here would go to minus infinity. So in fact 0 plus takes you to minus infinity. So we can draw that. This goes to minus infinity. So there we are. This pass band now moves from, let's call this omega SL. This point, where the edge of the stop band maps. So the stop band now maps between minus infinity and minus omega SL. And minus omega SL is of course behind minus 1. Further, what happens to plus infinity? Now plus infinity maps clearly to 0 minus. So plus infinity maps to 0 minus. 0 minus means, so when you say plus infinity, you mean a positive number that grows without bound. So when you do minus omega p by omega, if omega is a positive number that grows without bound, this would tend to a negative number that becomes as small as you desire in magnitude. That is what you mean by 0 minus. And therefore, the pass band is brought between minus 1 and 0. The stop band is taken between minus infinity and omega SL. And that indeed is what you expect for a low pass filter. That means we have transformed, the high pass filter is thus transformed to a low pass filter as follows. Plus 1, of course there is symmetry. So the pass band is brought between minus 1 and 0 and therefore also between 0 and 1. The stop band is brought between omega SL and plus infinity and minus omega SL and minus infinity. Remember, the pass band and stop band are carried as they are. The dependent variable is carried as it is, that is not affected. So when you bring the frequencies from omega to omega L, no effect is seen on the dependent variable that is carried. That means the tolerances are carried as they are. So that those are unaffected. So if you desire a certain set of tolerances in the high pass filter, the same set of tolerances are carried into the low pass filter. Tolerances carried as they are, carried as is. And of course omega SL is omega p by omega s for the high pass filter, where omega p is more than omega s. Yes, there is a question. So the question is, would the maximum value of omega be pi? Now please remember that we have already come to the analog domain. So what was from 0 to pi has now been brought to 0 to infinity by the bilinear transform. So now we are no longer dealing with the discrete angular normalized frequency. We are now dealing with an analog frequency which has emerged from the bilinear transform. Yes? So much so for the high pass. Now you see, therefore the high pass filter design problem is easy to formulate now. Design a low pass, a corresponding low pass filter with pass band edge equal to 1, stop band edge equal to omega p by omega s. Pass band, stop band, tolerances and nature carried as they are. As are. What I mean by that is, if the pass band is monotonic, let it continue to be monotonic in the low pass filter. If the pass band were equiripple, let it be equiripple here. So too for the stop band. And that means you now have the tools to do it. You can design it using the Butterworth approximation or the Chebyshev approximation, or if you are trying out any of the other two, inverse Chebyshev or elliptic, you could do that. And then all that you need to do is so having designed this low pass filter, the next step would be to make a frequency transformation. So then transform SL, that is the complex frequency variable of low pass filter, or Laplace variable of the low pass filter using omega p by s. Replace SL by omega p by s and you get the high pass filter that you desire. Yes, there is a question. So the question is, how do we prove the tolerances are carried as they are? We don't need to prove anything there. You see, what we are moving is the independent variable. Now, what value the function takes at that independent variable is unchanged. All that you are saying is that I am evaluating the function at this value of the independent variable, and that is anyway specified in the original filter. So I am saying the whole dependent variable is carried as it is. There is nothing to be proved there. You just have to note that you are making a transformation on the independent variable, and there is no change of the dependent variable at every given point. That is carried as it is. Alright, now having made this transformation, omega SL replaced by omega p by s, we now need to check whether we have obeyed the other two requirements of rationality and stability. Now rationality is obvious. This is a rational transformation, so if the original low pass filter is rational as it is expected to be, then this transformation would retain the rational character. So rationality is not a problem. But stability we need to check. So we need to check what this does to the real part. So let us consider S to be sigma plus j omega, whereupon SL becomes omega p divided by sigma plus j omega, which can be rewritten as omega p into sigma minus j omega divided by sigma squared plus omega squared. And therefore, the real part of SL is omega p sigma divided by sigma squared plus omega squared. Now it is very obvious that if sigma is positive, so is the real part of SL, because omega p is a positive quantity and sigma squared plus omega squared is bound to be positive. If sigma is positive, then sigma squared plus omega squared has no choice but to be positive. It can't be 0. And omega p is positive, so the sign of sigma is carried to the real part of SL. If sigma is positive, the real part of SL is positive. If sigma is negative, the real part of SL is negative. And therefore the left half plane goes to the left half plane and the right half plane goes to the right half plane. What it means is, you cannot possibly have poles coming to the right half plane if you did not have them in the first place in the low pass filter. That is because a point of the right half plane in the filter of desired nature goes to a point in the right half plane of the low pass filter, and that could not possibly have been a pole. And therefore, the poles can only be in the left half plane. In fact, we have also excluded the imaginary axis, because the imaginary axis goes to the imaginary axis. So the danger of poles going onto the imaginary axis also has been precluded in this process. Anyway, so that completes the design of high pass filters. And now we would like to look at the corresponding transformation for band pass filters. Now for band pass filters, we need to think a little more. You know, for band pass filters, it is very clear that you have multiple stop bands. Even though there is only one pass band, there are multiple stop bands. How on earth could you get multiple stop bands from a single stop band? You can't do it by a single element. In fact, here we can probably take a cue from what we do in LC networks again. Remember, we are going to choose an impedance of an LC network. Now, what simplest form of an LC network can give us an impedance which has multiple mappings? That is, you want multiple frequencies to have the same magnitude. That's the kind of mapping you want. You want the stop band to go to multiple places. How on earth can that happen? That can only happen if you have a second order system, at least. It can't be less than second order. But we can probably make do with second order. Now what we mean by second order is you need an inductance and a capacitance to come together. So let's consider a series LC network and consider its impedance. So we have an L and a C, and of course we have Ls plus 1 by Cs. So that gives us LCS squared plus 1 divided by Cs. Now we can divide by LC in the numerator and denominator, and that gives us S by L, which we will write as S squared plus omega naught squared by Bs, where omega naught squared is 1 by Lc and B is a positive quantity equal to 1 by L. Let us consider this transformation. Now omega naught squared, which is 1 by Lc, has a very important physical significance. In fact, all of us would probably be aware that for an LC network, that corresponds to what is called the resonant frequency of the network, the resonant angular frequency of the network. In fact, it is that frequency at which this impedance vanishes. So, you see, the interesting thing is that B also has a significance, but that significance we may not all be aware of, and let us not be too worried about it for the moment. We will see it in the long run. At the moment, we will just regard B as a positive quantity. It is the reciprocal of L, so 1 by L. So let us consider as a candidate SL to be replaced by FBPS, where FBPS is S squared plus omega naught squared divided by Bs. And let us go through the exercise first of checking for the, now we will do it the other way. We will first check property 1, then property 2, and then we will look at property 3. So of course property 1 is obvious again. This is a rational transformation, rationality is going to be maintained. So if the original low pass filter is rational, this has, the transform filter has no choice but to be rational, because you are replacing SL by a rational function of S. So rationality is maintained anyway, there is no problem with that. Now we need to look at the second property, stability. So all that we need to do is to substitute S equal to, in fact, we can do something simpler. Let us divide this into two parts. Let us write this as S by B plus omega naught squared by B into 1 by S. And now let us substitute S equal to sigma plus j omega. And then we have SL becomes sigma plus j omega divided by B plus omega naught squared by B into 1 by S, which is sigma minus j omega divided by sigma squared plus omega squared. And therefore, if you write SL as sigma L plus j omega L, then sigma L is 1 by B times sigma plus omega naught squared by B into sigma by sigma squared plus omega naught squared, or by plus omega squared. The real part, we are taking the real part out. This is the real part of this quantity and this is the real part of this quantity. So we have extracted them. Now you see it is obvious. If sigma is positive, then this has no choice but to be positive, and neither does this. Because 1 by B is positive, omega naught squared by B is positive. If sigma is positive, sigma squared plus omega squared cannot possibly be 0. It has to be positive anyway. And therefore, this is bound to be positive and so is this, and therefore sigma L is positive. On the other hand, if sigma is negative, then this is bound to be negative. And this is definitely bound to be non-zero, because sigma squared plus omega squared can't possibly be 0 if sigma is negative. It's bound to be positive. So this is positive, so this whole thing would become negative. So negative quantity plus a negative quantity would give a negative quantity. And therefore, sigma and sigma L necessarily have the same sign, strictly. So if sigma L is positive, if sigma is positive, then sigma L is positive. Sigma is negative, sigma L is negative. And in fact, right from here, we can also see that if sigma is 0, which means if you are going to the imaginary axis, then both of these quantities are 0, and therefore sigma L is 0 as well. And therefore, we also know what to expect on the imaginary axis. The imaginary axis goes to the imaginary axis, which is not a surprise, because anyway you are dealing with an LC impedance. So stability has been obeyed, and therefore we are guaranteed that if you have a stable analog filter designed, that would continue to remain stable when you go to the band pass domain. Now the question is, why should we call this band pass? And for that we need to look at the frequency, sinusoidal frequency transformation. So now let's look at what happens when S equal to j omega L only, S equal to j omega only. So of course that gives us SL, which is equal, it will give us j omega L, and j omega L is going to be omega naught squared minus omega squared by jb omega. That is j omega squared minus omega naught squared by b omega, and this is very interesting. So let's see how this behaves. Now let's consider some critical points on the frequencies. Which critical points we need to look at? Well, let's take a band pass. So a typical band pass filter would have a characteristic like this. It would have two edges of the pass band. Let's call them omega p1 and omega p2. Yes, please, there's a question. So the question is, what are we practically doing when we make this transformation? Now the answer is, all this is still in the phase of design. So we are not realizing it as yet. So all this is still design, and we are computing the filter coefficients. We have not yet reached a point where we have obtained the filter coefficients. We are yet designing on paper. After we have completed the design on paper, then we would translate it into a realization. So as yet all this design is in calculation. Right? So we have specifications for the discrete time filter. We have converted them into specifications for the desired kind of analog filter. Now we are going into the specifications of the desired kind of low pass filter. We will see in a minute. We will design that low pass filter. We will then convert S by using S equal to, by using the bilinear transform, and there we get a discrete time filter that we would try to realize. So realization is after completing the design. So there we have a band pass filter, and we assume as usual that we have tolerances. Now we are quite satisfied with letting the pass band be between 1 and 1 minus delta 1, and the stop band be not more than delta 2 in magnitude, and of course the nature can be specified. Now you see, you will have to decide on the nature of the stop bands here. There are two stop bands, so you can't have different natures for the two stop bands. Either both of them must be monotonic or both of them must be equiripple. We don't at the moment have a facility to allow different kinds of natures for the two stop band. Anyway, we do have a facility to allow different tolerances in the two stop bands. All that we need to do is, if the tolerances are different, consider the stronger of the tolerances. So for example, if one of the stop bands has a tolerance which forces it to be less than 0.1 and the other one must be less than 0.09, then it is 0.09 that you must choose in your design. Choose the stronger or the more stringent one, and then you can put that one. If you are satisfying 0.09, you are of course satisfying 0.1, so you will have to do that. Take the more stringent. Having done that, we can agree on a set of specifications like this. Let's put omega naught somewhere in between here. We expect omega naught to be somewhere in between here. And now let's see where this maps. You see, let's make a mapping of what are called some critical frequencies. So we have omega mapping to omega L. The critical frequencies are actually 0, omega naught and plus infinity, or rather 0 plus. 0 plus means a very small positive frequency which goes almost to 0. Now it is very clear, and the mapping of course as you know is omega L is omega squared minus omega naught squared by b omega. This is the mapping. Now it is very easy to see that omega equal to 0 plus, you see this is a little tricky. Now if it is 0 plus, then this is of course 0. This is minus omega naught squared by b into 0 plus. So it is minus infinity. Because you have a quantity in the denominator which is very small and positive. Here you have a fixed negative quantity. A fixed negative quantity divided by a very small positive quantity gives you an infinite negative quantity. What about omega naught? That is very easy to see. Omega naught maps to 0. That is very easy to see. And as you go towards plus infinity, now let us see what happens. You see, omega L can also be written as omega by b minus omega naught squared by b omega. So as omega goes to plus infinity, this quantity goes to 0 and this quantity goes to plus infinity. So therefore, omega equal to plus infinity goes to plus infinity. Now what happens in between? We have only taken the critical points. What happens in between? We need to see that too. So for that, let us write down this expression here. Omega L is omega b minus omega naught squared by b omega. So omega L is omega by b minus omega naught squared by b omega. So d omega L, you see this d omega L d omega is 1 by b plus omega naught squared by b times omega squared. So it is strictly greater than 0 when omega runs from 0 plus to infinity. That is obvious, because when omega is positive, then this is definitely positive. What it means is that as you increase omega from 0 plus towards infinity, you expect omega also to monotonically strictly increase. And therefore, going back to the previous table here, as you go from 0 plus towards plus infinity here, 0 plus is at minus infinity on omega L, omega naught is at 0 and plus infinity goes to plus infinity. So as you move omega from 0 plus towards plus infinity, omega L would move monotonically from minus infinity to plus infinity and omega naught would come to 0. Now you need to, you see the situation is like this. 0 plus would go to minus infinity. Somewhere in between you will have a mapping of this omega S1. Then you would have a mapping of omega P1. Then you would have 0 here. Then you would have a mapping of omega P2. And then you would have a mapping of omega S2 and finally plus infinity. It is going to follow the same sequence. Now, you see, we have full control on choosing omega naught squared and b to meet the specifications that we want. What are the specifications? The first thing is that you want a symmetric magnitude response. So this is going to map to some point on the negative axis and this is going to map to some point on the positive axis. You want them to be equal and opposite. So what you want first is that omega P1 squared minus omega naught squared divided by b omega P1 should be equal to minus of omega P2 squared minus omega squared divided by b times omega P2 for magnitude symmetry, for symmetric passband edge. Otherwise the low pass filter would have one negative passband edge and a different positive passband edge. We can't allow that. Now we can solve this. It's very easy to solve this. One can easily solve this. And in fact one would obtain omega naught squared is omega P1 into omega P2, which is very interesting. Now this is not at all a difficult equation to solve. It's a simple linear equation in omega naught squared, so you can easily solve it, and you would obtain omega naught squared is omega p times omega p. This is very interesting. What it says is that the so-called center frequency or the resonant frequency, as we chose it in the beginning, is the geometric mean of the passband edges. And this is not unfamiliar. In fact, if we take a typical LC network with a resistance added, by the way, then it is indeed true that the edges of the the points of half power as known do turn out to have a geometric mean equal to the center frequency or the resonant frequency. This is not surprising. This is indeed a property of a band pass filter as known with LCR networks. So this is surprising but true in this case as well. So omega naught squared is determined. Now what is it that would determine B? Actually nothing at all, but we can put something down to make our whole life easier. You remember in the high pass filter we had put down the low pass passband edge as 1. Now let's standardize that to make life easy. So we could put down the passband edge as 1, not just, you see what we have said so far is that the passband edge on the positive side and on the negative side must be the negative of one another. That is all right. But let's make that 1 and minus 1. That makes life easier. So let's put down let us ask for, this is our choice, let us ask for omega p1 to map to minus 1 or equivalently omega p2 to map to plus 1. That means omega p1 whole squared minus omega p1 omega p2, because now we have agreed that omega naught squared must be omega p1 omega p2 divided by b omega p1 should be equal to minus 1. That would of course very clearly give us b is omega p2 minus omega p1, and of course the same thing would follow if you put the condition on omega p2. So now we have an explicit value for B and for omega naught. So in fact our band pass transform is complete and we are now in a position to design band pass filters too. What do we need to do? Let's just put down the steps. We have this band pass filter. First step, take omega naught squared equal to omega p1 omega p2, b equal to omega p2 minus omega p1, and now we know why we call this b. B stands for bandwidth. So in a way b is the length of the passband. Having taken that, the next step is to design a low pass filter with the following specs. You see, omega S1 would transform to omega SL1. Omega SL1 is omega S1 squared minus omega naught squared divided by b omega S1, and similarly omega S2 would translate to omega S2 squared minus omega naught squared divided by b omega S2. Now omega S1 would definitely be negative and this would be positive. Take the smaller of mod omega SL1 and mod omega SL2. This is omega SL2. for stop band edge. You see, what we are saying in effect is that the pass band edge is of course 1, but this would give us one stop band edge here and this would give us another stop band edge. Which of them should we take? They may not be equal. So naturally you must take the stringent, the tougher condition there. Which is the tougher condition? The one which is closer. That's why we have taken a minimum here. So take the minimum of the modulus of SL1 and the modulus of omega SL2. Whichever is less, that means it's closer. Of course, both of them will be more than 1 in magnitude, that is for sure. But the one which has a smaller magnitude should be chosen as the stop band edge. So of course, now you know the pass band edge of the low pass filter, you know the nature of the pass band, you know the stop band edge of the low pass filter, the more stringent of the two. You know the nature of the stop band, you know the tolerance in the pass band, you know the tolerance in the stop band. So you can design the low pass filter using either the Butterworth or the Chebyshev or inverse Chebyshev or elliptic approximation, and then transform the low pass variable SL using S squared plus omega naught squared by Bs, where you know what omega naught squared and B are. With that then you would, yes please, there's a question.
What happened to the minus infinity to 0 interval?
Oh, so the question is, what happens to the minus infinity to 0 interval? Where the minus infinity to 0 interval, you see, it is very clear that minus omega, yeah, that's a good question. So let's just let's answer that. You see, one thing that you need to check is what happens when you put S equal to minus j omega here. You see, so we will see very quickly that this mapping must be odd. You see, the mapping, the frequency transformation is odd. So S equal to, so if omega goes to omega L, then minus omega would go to minus omega L. That's very easy to see. The mapping must be odd. Right? In fact, you can see it here. Omega squared minus omega naught squared by B omega. When you replace omega by minus omega, this whole thing is negated. So the mapping is odd. Isn't it? So therefore, whatever you are doing on the positive side of the frequency axis is mirrored on the negative side. And that anyway is required because you want magnitude symmetry. Is that clear? So with that then we have completed our design of the band pass filter as well. And now all of us are in a position to, of course, once you have designed the band pass analog filter, you can transform it using S equal to 1 plus Z inverse by 1 minus Z inverse using the bilinear transform. You have the discrete time filter with you, and then you can realize the discrete time filter as you desire. So now we have completed the design of band pass filters, and now all of us are well equipped to complete our assignments on the design of the band pass filter as well. And then we shall in the next lecture look at how we might design band stop filters, and with that we shall be well equipped to complete the assignment given to us on filter design.